Hey, chemistry. It's Monday, April 20th, and I'd like for you to turn to page 446. We're going to do chapter 13 in just a breeze. All right, page 446. We're talking colligative properties here. Do you see how this is steaming out? Well, my mom had a way of cooking eggs, and I remember as a little kid asking her, Mom, when you put the eggs in there and get the water boiling, then you go ahead and you sprinkle salt in there and the water quits boiling. Why do you do that? And she said to me, and I remember this like yesterday, she said, I don't have any idea why, but that's the way my mother did it. And that's the way we do this. We cook eggs by boiling water, and we be sure to put some salt in it. Well, now we know that that is colligative properties. What does that mean? It means when you make a solution out of the water, not just pure water, but a solution, then the solution is going to interfere with the vaporization. That is, if you look on 447, you see those little lavender bubbles there? Those lavender circles represent the salt that's in solution, that's interfering with the vaporization process. The water molecules cannot escape because this salt's in the way. And so what it does is it holds down the vaporization for a while. So that water gets hotter before it vaporizes. And so Mom knew that she was cooking the eggs not at 212 Fahrenheit or 100 Celsius, but she was cooking them at like 105 Celsius. So it raises the boiling point when you put a solution, a solvent in there. Lowers the vapor pressure, raising the boiling point, lowering the vapor pressure, meaning the vapor pressure is what's inside those little water bubbles that push their way out of the liquid and become a vapor. And that vapor pressure is lowered, it's held down, and that's because of the interfering factor. Same thing with freezing. Freezing is changed because when you put salt in there, can you see where the temperature is at 0 Celsius, 32 Fahrenheit? It's at 0 Celsius right now because that water is melting. I mean, that ice is melting. And so it's at the freezing point or the melting point, whichever you want to call it. But what happens if I put this salt in there with it? If I make it sort of the water that's on the side of those ice particles, if I make that water become salty water. If I make that water become salty water, what happens to the freezing point? Can you see that it's no longer at 0, but now it's already down to -7? So I would like for you, wherever you are right now, go like this. Boink, boink. You got to go boink, boink. And so what happens when you put the salt in boiling water is that it raises the boiling point. And when you put the salt in the melting ice, it lowers the freezing point. So that's colligative properties. And the more salt you put in, the higher the change in the boiling point. And the more salt you put in, the lower depression, we call it depression. The greater the depression of the freezing point. It all has to do with the concentration of the salt. And so colligative properties on page 446 is properties that depend upon the concentration of the solute particles, but not on their identity. Those are called colligative properties. And you express it in terms of molality. The greater the concentration in molality, the greater the boiling point elevation. That's a property that will change because of the solution. And this is a freezing point thing. Now you wonder, why do you put salt on an icy road? Well, when you put the salt on the icy road, the ice says to the other ice, ooh, this is now a solution. So we're not supposed to be melting yet. We're supposed to be melting at a lower temperature. We need to, wait. What the ice says to the ice is, ooh, we're supposed to have a melting point which is lower. So we should have already been melted. And so the ice melts. Because the freezing point depression pushed that freezing or melting point way down there. And the ice says, oh, it's only 0 degrees out here. It's only 32. And so therefore, we're at a point where we should already have been melted. Let's melt. So it's called a colligative property. And that's the picture on page 446. The end of chapter 13. Oh, by the way, go to 452. Osmosis is also a colligative property. Osmosis, you learned that in biology last year. It's where water comes and goes through a semi-permeable membrane around every cell in your body. And if your cell has within it too thick of a solution, then water will enter. But if inside it is too thin of a solution, the water will leave in order to keep that cell at exactly the right concentration with water and all of the minerals that are dissolved in it. And so osmosis is the movement of solvent through a semi-permeable membrane from the side of the lower solute concentration to the side of the higher solute concentration. In other words, it's all about water flow. Which way is water going to flow? And it always flows towards the thicker stuff in order to thin it down. If the thicker stuff is inside the cell, it goes that way. If the thicker stuff is outside the cell, I know, more concentrated, then it goes that way. And it does it naturally because God made it that way. Okay, so it looks like I've done about 8 minutes. And I'm going to go ahead and I'm going to go on over to acids, bases, and bases on page 467. I'm going to do about another 5 minutes. Okay, I'm on 467, everybody. Sour milk contains lactic acid. We've got rotten apples or whatever, fermenting process. That's called acetic acid. That's vinegar. And we've got some hydrochloric acid, and that's called muriatic acid in the store. We've got some baking soda, which is a base. So we got acids that are weak acids, vinegar, and strong acids, hydrochloric acid. We got bases, and they produce hydroxide. These produce hydrogen ions, and these produce hydroxide ions. Okay, this is a salt. That's not an acid or a base. This is ammonia, NH3, and it's dissolved in water, so it's ammonium hydroxide. Anyway, it produces hydroxide ions. This is a weak base. So is this, and this is a strong acid, and this vinegar is a weak acid. And the weak versus strong has to do with how the percent ionization, how much does it break down into ions to form electrolytes, that kind of thing. All right, we've talked about that. On page 467, you see some acids on the left, and that would be like citric acid for the lemon, phosphoric acid, and carbonic acid in the Coke. And the apple juice back there is, I think, called malic acid. And then the strawberries, of course, they're citric acid. And over here on the right, you've got ammonia and you got lye. Lye is called soda lye, and it's very caustic. Caustic means it'll kill skin cells. It's Drano, if you please. It's called sodium hydroxide, NaOH, and it's called soda lye. And then there's the baking soda, and then there's the antacids, aluminum hydroxide. Okay, acids on page 468, they got 5 features of acids. One is if you make a solution in water, aqueous solution, it's sour. Think about lemons. And it's also corrosive because it can break down body tissues. Now look over on page 471, point number 1. That's the bases, page 471. Under bases, they are caustic and they are bitter. So while acids kill skin cells and they are corrosive, bases kill skin cells and they are caustic. Why do they have two words for the same thing? I have no idea. Acids are sour and bases are bitter. In fact, go back to acids on page 468. They changed the color of indicators. When you put, let's see, acids turn red. So they take blue litmus paper and turn it red, while bases take red litmus paper and turn it blue. And I think you see the picture on 468, and you see the picture on 471. Okay, number 3, acids, back to page 468. Acids react with active metals and release hydrogen. You know about that already. It was called the activity series. Number 4, acids react with bases. And what is the product of acid-base neutralization? It's salt and water. Okay, number 5, acids conduct electric current. Why? Because acids produce ions in solution, and therefore they are electrolytes. Okay, do you know how to name acids? You've learned this way back early in the year. On 468, HF is called hydrofluoric acid. It's a binary acid. On 469, Chaku, CH3COOH, is acidic acid. It includes the acetate ion and a hydrogen. And remember adic-itis? That's how you name acids. Those are oxyacids on the right there. And oxyacids mean it's a hydrogen combined with a polyatomic ion, which includes oxygen. And sometimes they're called ternary acids because they have 3 different elements instead of just 2. If you look on 470 and 471, you see the uses of many of the acids. And I'm going to summarize the bases right now on 471 and 472. Bases are bitter in aqueous solution, and they turn litmus paper blue, or indicators a different color, and they are slippery. Soap is made out of sodium hydroxide, soda lye, and soap is slippery. So it's all the B words: bases, bitter, blue, slippery, and they give you what we call a big pH number. There's a scale called the pH scale. It goes from 0 to 14, and 7 is neutral. And the big numbers are the bases, and the small numbers are the acids. Okay, I'm on page 473. An Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions. So let's take this as an example right here. And we're going to go ahead and see how it does that. We talk hydrochloric acid, and you put it in water, and it forms hydrogen ions, and it forms chloride ions. In solution, we talked about this when we talked about electrolytes. Electrolytes are acids, bases, and salts, but this chapter is dealing with just acids and bases. All right, I did it red because it turns litmus paper red. By the way, the acids are just the opposite of the bases. The acids are not bitter, they're sour. The acids turn litmus paper red. The acids are not slippery, and they're not a big pH number, they're a small pH number. Okay, and so now let's go with acids. That was acids, red. So let's go blue with the bases. Let's go sodium hydroxide, which was soda lye, and let's put it in water. And let's find out what ions it produces. Sodium ions, and there they are, hydroxide ions. Hydroxide ions, according to Arrhenius, in water solutions produce bases. And hydrogen acids in water solution produce hydrogen ions. See ya.